Just to remind you, the homework assignment, which is we're going to talk about quantum mechanics. And we started the discussion on Friday. We'll continue that today because later, in particular, alpha decay and beta decay. And what I like to do at this point is to show a little video. This is a cute video that my son actually pointed out to me that's available online. And it talks about one of the most, just get a chair from across the hall. There is all of the myths of quantum mechanics. Now, it's done in a sort of humorous way, and some of it is a little bit far-fetched right at the end. We'll talk about that. But basically, everything it shows is absolutely true. Okay, so I'd like to show you that. Hopefully this works. Actually, let me get organized here. We'll try to capture the audio from the video. See if this actually works.
And here we are.
Hang on a second.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay, it gets a little hokey at the end there, I'll give that to you. The electrons don't know anything and they don't behave differently. But the point about the observation is absolutely true. And everything they said in that movie, except a little bit at the end, is absolutely true. It's really been done with one electron at a time. I think there's something neutrons, one neutron at a time. And if you don't like that, they've been done with neutral atoms, one atom at a time. And that interference pattern is really what you see. So, like it or not, and you can think about this experiment all you like, it's a great thought experiment, a great real experiment. It really contains in it all the mysteries of quantum mechanics. Any questions about that? Okay. So let's go back to the lecture. Yes, so you're asking about how do you know which slit it actually goes through and why that influences the pattern on the screen. Ethan, how are you observing me right now? Your detector. In fact, you can see those little dots on the screen if you make it a phosphorescent screen. But I'm talking about what is it that allows you to see it all? It's light, okay? So what's happening is sunlight is coming in, bouncing off of me, being reflected into your eye, electron, and determine which of the slits it goes through. It is to shine photons on it, okay? The photons tell us where it is in position, and that would allow us to tell which of the two slits it went through. The electrons are so small that in order to localize the electron to within the dimensions of those two slits, you need photons to do that. And what we're going to see later on, the photons bounce off the electron, they disturb it. They transfer momentum to the electron. And so that action of observing affects where the electron is, because what you see is not where it ends up. And that interference actually makes the pattern appear. So when you shine the photons on, you interact with the electron and thereby disturb the interference pattern and turn it in from that interference thing to the two distinct bands. And anything you can do to try to localize the electron will cause that interference pattern to disappear. So that's what they mean by the active observation collapsing the wave function. We're going to see today that the only thing you can ever know about any quantum system is the wave function that describes it. That wave function, you can calculate probabilities for things to happen, but you can't know with absolute certainty anything. That's one of the features of quantum mechanics. You set up a system identically many, many times and let it come. There will be a distribution of outcomes, and the wave function allows us to calculate the probability for each of those outcomes to be as much as we can do. Okay. So quantum mechanics. So quantum mechanics in the early 20th century, there were hints about it earlier to look at things like decay, and that there was a process known as the photoelectric effect where photons materials, and it was hard to understand why the experiments produced the results if behave like optics. So in about 1924, this gentleman, de Broglie, came along, and in his PhD thesis, he introduced the idea that all particles have both physical and like properties. This was a very radical idea back then, and what he did is he assumed wavelength lambda. The wavelength of that particle is Planck's constant h divided by the momentum of the particle. And soon after this idea was with electrons, very much like the ones I just showed you in that video, were that electrons really do have diffraction patterns, and the only way it could be explained is if they have these wave-like properties. So there's a conflict in our understanding that we like to think of as particles, these little billiard balls or bowling balls or BBs, which we think of as being localized. We think that we can identify where an object is very well. On the other hand, they also have wave-like properties, and a wave by its nature isn't localized. It has a very large, if not infinite, extent. And unfortunately, the objects we're dealing with here, the electrons, protons, and all the particles, kinds of try to understand what the implications of that are for nuclear physics. Around the same time, this gentleman was thinking about similar problems. This is Heisenberg, and this idea of particles having wave-like and particle-like properties. What he figured out was that as a result, it's not possible to precisely determine several different properties of a particle at the same time. In particular, if you try to localize the position of the particle, as in that slit experiment, so we could tell which of the two slits it actually went through, you can do that, but because of photon or whatever other probe you're going to use with that electron, you disturb its momentum. Came up with a quantitative relationship that the uncertainty in the momentum of an object times the where h is constant, and the h bar means I've taken Planck's constant. That's one form of what's known as the Heisenberg uncertainty relation. Another way to write times the uncertainty in the time over which you make the measure is also, that product is also seconds. Normally we don't see that because it is so small, but in the quantum world it makes a difference. Now we're going to do some to figure out how to use these numbers. Certain combinations of physical constants are going to come up over and over again in the course of this semester, and it's useful to remember them. There are very few numbers you have. Two I highly learn. First is the product h bar c. Okay? Planck's constant divided by 2 times the need and use. That'll turn out to be a useful set of constants. And then the other one, electron. That ratio E squared over h bar c is often written as alpha. It's a dimensionless constant. That is, all the units cancel out there if you actually go through the arithmetic. And it equals 1 over 137 approximately. And that's another useful number. Show you as we go along. Okay, so let's see an application of the uncertainty principle. Suppose I have an electron, and I try to confine it to a very small region of space. atomic nucleus. Okay? We've seen the other day that atomic nuclei have dimensions on the order of femtometers, and a big one might be 10 to the... Okay? An electron, plunk it down in a box, which is 10 femtometers across. You might think, oh, it just sits there. What Heisenberg says is, no, that's not true. By the fact that you've confined it, you force it to move. That's what that uncertainty principle means. What it means is there's a minimum momentum associated with confined it in this small. And how big is that momentum? Well, I could bar over 2 times. I've just femtometers. 0.511 MeV over c squared. Fast. Kinetic energies on the order of MeVs or so. To describe them. And in fact, in the extreme case, where you have very high energy electrons, we can even neglect the rest mass energy when we're talking about what their energy is. And so we c is the speed of light. Now I'm going to energy of electron. So that's h bar c divided by 2 times things. Here, as you can see, why I'm going to use that h bar c complex. 7 MeV femtometers, and I divide by 20 femtometers, which is 2 times the size of the box. And what I find is that delta PC is 10 MeV. And as I was saying before, that's large compared to the rest mass energy of the electron, so I can basically neglect it and say the energy of that electron. So just because I've confined the electron to the box, I force it to have a high energy. Okay, that's what the uncertainty principle is. And this is a bit in comparison to the typical kind of energies we see in nuclear beta decay. Those are more like 1 MeV. So what this is saying is, first of all, we can't really confine electrons in the nucleus. They would rattle out right away. There was an early model of atomic nuclei, which was proton. The neutron was discovered, and is one of the ones that kind of killed that model, because you can't actually keep an electron alive because it's possible. So we're forced to accept quantum mechanics, and the way we're going to describe things in nature is through use of a wave function. And the way we figure out what these wave functions are, you've seen before, called Schrodinger's equation. How many of you have not seen this? Great. Very okay. Almost everybody has seen it. We're not going to need a whole lot of stuff to do it in, but I'll do the basic stuff that's absolutely necessary for. Okay. So the wave function defines observable property system found was you can use everything's in 1 dimension. Generalize it to 3 dimensions later. So you've got a system, spatial variable x is the tribe. And then I add to that whatever potential, and we'll talk about the potentials we have later, that might be functions of position, times, and that combination of operations in the wave function system times the wave function. Okay? It's called an eigenvalue problem, because I have a function psi, I do some operation on it, and as a result of doing that operation, I get a number, which in this case is the energy, times the original wave function. What we're going to see in a minute is that solutions of this equation exist only for certain values of E. That is, in most situations, any energy, not every energy, is allowed. Only figure out how those energies are calculated in a few minutes. So you notice here we're only talking about spatial wave function time dependent by adding an extra term. So part, and I multiply it by e to the I omega t, where omega is a frequency, which we'll also calculate in a little bit, and it's related to the energy. It's the energy divided by h bar. Okay? Now, what do we do with this wave function? We haven't figured out what it is yet, but wave function and its complex conjugate. So wave functions are generally complex objects. They have a real and an imaginary part. The product of the wave function and its complex conjugate is what. This is the thing that allows us to calculate quantities. So, for example, in two places, x1 and is given function, multiply it by a complex conjugate. I integrate that over our one spatial variable between the limit. Okay, so what is the particle between x1 and x2? It's psi star psi dx integrated from x1 to x2. Remind you what we mean by complex. I, where I is the square root of -1. And then the complex conjugate is bi. So the wave function is a useful thing because we're going to be able to calculate where particles are. Okay? To infinity, that quantity better be 1 because the particle is somewhere, although I may not know exactly where. And that's what's known as the normalization condition. And that will be useful later on to determine quantity wave, the total probability of 1. The position of an object is not the only thing we're going to want to know. We might like to know its momentum or its energy. Value or an average value. As I was indicating before, this is all you can ever know. What is the expectation value or the average value of a particular? So if that quantity is f, is to sandwich that thing, f, complex conjugate and do that integral. And the thing we're actually going to use is what's called an operator. Functional, it's something which operates on the wave function. And that's what we end up integrating. So, for example, there is a component of the momentum. It's the x component. The object. Plug that in here, and I do the integral and find the average value of that. Now, particles are moving around. We can think of particles traveling from left to right or right to left. Like you think of, and we'll use this in quantum mechanics as well. You can calculate a current density, basically the number of particles going the other way. That's the net current flow through. So if I'm sitting at a difference by this current density, and in terms of wave functions, the times the complex conjugate of the wave function if you think about it, psi represents particles going one way, psi star represents particles going the other way, because of that e to the plus or minus I omega t business. And if you're ready, just to remind you, which again, everyone has seen. Theta and e to the minus I theta is cosine minus I sine theta. Everybody's seen that before? Okay. And I is this funny square root of minus 1. Okay. So with that kind of general, looking at real problems in one dimension. And we'll start simple and we'll get more complicated as we go along. The simplest possible problem is free particle. Okay? And what it means is there's no potential anywhere. I just have a free particle in free space. So if you go back a minute ago and just put in that the potential everywhere is exactly 0, then Schrödinger's equation reduces to this. It's a simple second-order differential equation. Second squared is just minus 2 times. So hopefully that's something, again, you've seen before in a class in differential equations, that you're looking for a function that has the property when you take out front. And so if you think about it, those are sines and cosines. Or if you like, they're e to the I x's and e to the minus I x's. So the solution x, where k is a number we'll discuss in a second, x's, you'll see back. So that number twice the particle times its energy divided by h squared. Dependent form of the wave function, and if I'm time dependent, I just add on an extra e to the I omega t, or e to the minus. And so it's a function of position and time, and it's a number c, and that number will depend on certain conditions we'll see in a little bit, times e to the I kx minus omega t plus another number d, e to the minus I kx plus omega t. And what this term is representing is particles that are moving that way in time, and this term is representing particles moving the other way in time. Okay? And so suppose I have now a source of particles. I have a machine which is spitting out electrons, like in that video, for example. And the machine is sitting at minus x equals minus infinity, and it's shooting particles out that are going in the plus. So the machine's over there. It's shooting particles out that are moving from my left to my right. So it looks like shown here. And they all have a certain momentum, p. So what that tells me right away, if I go back to this wave function, is the other way. And in this example I'm giving you, there are no particles doing that. All the particles are going that way. The way that can be is if this coefficient is 0. Okay, because there are no particles going that way. They're only going that way. And that's how you initial conditions to try to get information on what these coefficients are. So then we know that the wave function is simple. And just plugging in this wave function with just the first term there into by that machine shooting particles from my left to my right. Simple derivatives, and then do a little bit of arithmetic, and what you find about it. H bar k is what we said was the momentum of the particle, and the momentum divided by m, at least classically, is velocity. So this is velocity, and this is a measure of how many particles there are. So that's why we get a nice number for the current, okay, for this simple example. as it gets. A system potential is just free particles. The wave functions look like sines and cosines, or e to the I, kx, e to the minus. Okay, next simplest. Potential. And what this means is in the region left of x equals 0, free particle system about a minute ago. And then there's a boundary at x equals 0, and there is a step potential, meaning it rises instantaneously from 0 to some value, which is called. It's like there being a hill, okay, a very steep hill all of a sudden, okay? 8v0. So, like this, for x less than 0, it's just 0. For x greater than 0, it's a constant, which we call. For x less than 0, this is the problem solved. So the wave function we can write down right away. And this is what k is. In the region where x is greater than 0, it's not into Schrodinger's equation. And it gets rewritten this way. And what we're going to do in all of these kind of cases is we're going to try to solve Schrodinger's equation in pieces, and then we'll put the pieces together. So in this kind of problem, there are two obvious different areas of space. There's the area for x. That's one region of space where the potential is a constant and happens to be 0. Again, the potentials Schrodinger equation in each place, and then we'll match them together. So this is the solution in region. Now here's region 2. Squared. Zero. E is the energy of the particle, and V0. That. And for now, we're going to assume that the total energy of the particle is greater. And so, for this picture, what that means, as I've shown over here, the energy of the particle is bigger than the height of the barrier. What that means is the particle can keep on going. Okay? Classically, if the energy were less than the height of that barrier, what would happen? Suppose the wall were higher than through it. It would reflect back, okay? You're running into a brick wall. If I threw a ball against the wall, it would just bounce back. We're going to see in quantum mechanics is that even if the wall is very, very high, the particle still has a chance of getting through. That's what this quantum mechanical tunneling is that I talked about the other day. Over the barrier, and quantum mechanically it can too, although as we'll see, there's still some consequences for being there. Okay. E is greater than V0. We get the original function back with a number. It's just a number because remember, at this point, we're assuming that that potential is a constant. It's just a number. The thing which multiplies psi2 is just a number, and therefore the numerical form of the solution looks the same as the solution in free space. These coefficients are going to. I can write that psi2, the wave function that describes the particle in this region 2, e to the minus ik2x, and the only difference between the solution here and the solution in free space is k2 is now different, because now the quantity that comes in is this e minus v0. Okay? So I've got a wave function in free space, I've got a wave function in the region where the potential. And the reason I have to do that is that this wave function is supposed to. That means the wave function and its first derivative must be continuous at any boundary. The wave function as I go across that region from v equals 0 to v equals v0. Furthermore, the first momentum of the particle is related to the first derivative, and the momentum has to be a continuous function. Okay. So at x equals what that means is I have two conditions on my wave function. Okay. So if I go back now, sorry. Okay. So here's go to region and plug in x equals 0. These are going to go away. This is going to go away. I'm going to have c plus d. And so what that means is if the wave function is going to be continuous, that a plus b better equals c plus d. Okay, that's the nature of the wave function. And similarly, if I take the first derivative in region 1 and the first and go through the arithmetic, what you're going to find is that k1 times the quantity a minus b has to equal k2 times the quantity c minus d. Okay? Imagine we're seeing a problem like the one I had, and the problem is that I've got particles towards the right. And that'll allow us to restrict these quantities a, b, c, and d. Reflected wave. So from left to right. B is a measure of reflected wave. Now, classically, there wouldn't be such a thing, right? If this thing behaved as a particle. But if you ever did a ripple tank experiment where you have water and you have a tank which has varying depths, you'll remember that there's actually a reflected wave that gets produced when the wave goes across that boundary depth. That's what's meant by this term, B. C is a measure of the particles that keep on going in the same direction they were originally traveling. And D would be particles that originated from the right and moved toward the left. Okay? We don't have any particles that started out on the other side and were moving towards the barrier. So D is 0 in this particular problem because of the way we go through the got these two conditions on A, B, C, and D. What I can find, and I'll leave it up to you to do the arithmetic, it's just simple. It's 1 minus k2 over k1 divided by 1 plus k2 over k1, where k are those wave numbers. A over just the number 2 divided by 1 plus k2 over k1. This definition now the wave function is, and we can calculate of the particles that are incident on that, even though classically they have enough energy. And that reflection coefficient is just the current that is reflected divided by the current that comes in. And definitions of the wave function, that's the k2 over k1 all squared. If you like, the probability that the particle bounces off the barrier and gets reflected back to where it was coming from, and the direction is again the transmitted current divided by the incident. That's k2 over k1 times c squared over a squared, and if you go through the arithmetic, this is what you get. So unlike classical mechanics, where I had a particle encountering a little hill and all the particles would keep going, I end up with back in the towards their and a certain number that are going in the same direction. Particles are not created in the process, so I better make sure that the total number of particles is conserved. And in fact, if I go through the arithmetic and add up R and T, that is the reflection coefficient and the transmission coefficient, that again reflect probability to find. And if you just go through the arithmetic, you'll see that adds up to 1. Particles are being conserved in this case, as they will in almost all cases we deal with. Okay. Okay, it's going to get more complicated. So the next level of complication is here, and this is beginning to look like a nucleus, okay? The other things are not real nuclei. This is something that could be kind of a nucleus. Look at this. This is what's called a particle in a square. One, but the meat in Appendix B. So the situation we're talking about looks sort of like this. There's a region of space. It's minus a over 2 and plus a over 1 dimensional variable x. Potential that we've done before. And that barrier extends from minus a over 2 up to plus. Okay. If the walls are infinitely high and I plunk a particle, what's the chance of finding it out here? 0. And what's the chance of finding it out here? 0. It can't get out. Okay, even can't get out. Because the barrier is infinitely high, it's infinitely thick. Okay? If it weren't infinitely high and it weren't infinitely thick, even if I plunk the particle down there, it'll leak out. Okay? But because of those two conditions, infinite height and infinite width, the particle's really stuck in the box. Look at the box, it just sits there. But because of Mr. Heisenberg, it okay, restricted A, and therefore it has to move. That's what Heisenberg really says. Okay? Region. Solve the problem in these two regions of space. So inside the box, it's a free particle. We've done this twice now. Okay? So we write down Schrodinger's equation. It's just minus h bar squared over 2m, second derivative of the wave function. Write them in terms of sines and cosines. You can equally well write sine kx plus b sine kx, where k is related to the energy. Okay, that's the wave function. Now, we've got some boundary conditions here, which is, as I said, the wave is continuous, therefore these functions need to go to 0 nicely when I hit the boundary. So what that means is that the wave function evaluated at x equals minus a over 2 or 2 better be 0. That will guarantee that the wave functions match, because the wave function is uniquely 0 here. What just putting in a equals x equals plus a over 2 or x equals minus a over 2. So psi of a over 2 equals a cosine ka over 2 plus b sine ka over 2, and that better be 0. And similarly on the negative side. And so what it means is that a times cosine, and I can add those two equations together if you like. So I add those two together and that gets rid of the b's. So then I'm left with a cosine k over 2 equals 0. Or I could subtract the two equations from each other, and that would get rid of the a's. And that gives me b sine ka over 2 equals 0. So one trivial solution is a and b are 0. But that would mean there is no particle. Okay? Particle that I put in the box. A or b non-zero. So let's suppose, first of all, that b is 0. And what that means is what that means, Ka must equal n pi, where n is Ka. I plug it into that expression, so that's pi over 2, and I take the cosine of that, that's 0. Okay? So that would satisfy the equation. Similarly, if n equals 3, if Ka n, cosine of that is 0. So that will nicely satisfy the equation. That's if b equals 0. If so that sine Ka over 2 equals 0. And that also works for Ka equals n pi, but now n has to be an even integer. So for example, if n equals 2 and I plug it in there, I get sine of pi, and therefore 0. Okay? So there are two sets of solutions then, signs. And if you've got one, you've got odd integers, and if you've got the other, you've got even integers. Now we know how to now is h bar squared pi squared over 2ma squared times this integer n squared. So what this is saying is simply by plunking the particle down, and the energy levels are now quantized. Okay, there's a discrete set of energy levels. N can be 1, it can be 2, it can be 3, and that defines level. Okay, so the energy is not continuous anymore. They're discrete states just because I've confined the particle in the box. That's something you would have classically. Now, just to finish up the discussion, to figure out exactly set it up in the box. It can't be outside. So if I take the wave function and square it, and now we're considering wave functions that are strictly real. I write them sines and cosines. So psi squared integrated from particle capacity, which is minus a over 2 to plus a over 2, better add up somewhere in that darn box. So if I consider just the solutions of the wave function, I would write down that this quantity squared, psi squared, would look like a squared sine squared n pi x over a. Favorite table of integers, look up x, and I find is it equal to minus 1 over 4 alpha. This particular equation into this general form, and I find that a squared times this quantity, a half x minus a over 4 n pi sine of this thing, evaluated between minus a over 2 and plus a over 2 equals 1. Minus a over 2 and a over 2, this term goes away, and I'm just left with a half x over there. A over 2. So a squared times a over 2 has got to equal 1. That tells me that a is just a number. It's a square root of 2 over a. And so then I get to write down the final form for the wave function. Psi of x equals root 2 over a cosine n pi x over a for odd integer values of n. And it's equal to root 2 over a sine n pi x over a for even integer values of n. And the reason I went through this is and integrate them, I always get 1, meaning the particle is somewhere. And if you think about what that means, wave functions look like. So here's my box that goes from minus a over 2 to plus a over 2. One, it's going to look like a cosine term, and so the wave function is going to be 0 over here, 0. Okay, and there'll be an energy associated with that that I can calculate by just to this expression and plugging in equals 1. So that'll be the lowest energy state. That's the lowest possible energy it can have, which is not 0. Okay, so again, just by sticking it in the box, and calculate what is the probability to find it in any region of the box. So I could ask, what's the probability to find it between a over 4 and a over 2, for example, given that functional form? Now you know how to calculate it. The next term there, psi 2, that's when n equals 2. And now it looks like a sine wave, okay? It's 0 at the middle. So even though you plug place to find, in fact, that wave function has 0 probability to be there, okay? It has probability over here, but not at the midpoint. If you're at n equals 3, it'll be the next wave function. And each one of these has a discrete energy associated with it. So this will be the lowest energy, that'll be the next lowest, and so on. Neutron protons inside. By the fact that they're going to be confined inside the nuclear, can't be at rest, they have to be moving, and there'll be quantized energy levels. Complicated as nuclei are not, okay, they're more complicated than that. And we'll see how the property of having quantized energy states to calculate. Okay, I think I'll call it quits for today, and hopefully this is enough information to finish up all the homework. See you Wednesday.